Welcome to our online seminar. We have today a particular situation. Our speaker, Guoyin from University of New South Wales, is of course a good friend. He received his PhD from the Chinese University of Hong Kong, 2007, and then he moved to Sydney, Australia. And this means that in order to honor our invitation, he has to give a talk at 1:30 in the morning. So it is Tuesday in Australia. Thank you, Guoyin, for accepting our invitation. So it is great to have you in our seminar. So Guoyin is an expert in many areas of optimization. So of course, he obtained a lot of nice results on theoretical topics related to duality, robot optimization, SDP, but then also related to numerical algorithms. And in particular, in the last years, he had some contributions on so-called Kurdyka-Lojasiewicz calculus. He wrote some papers with quite strong impact. And the topic of his talk today will be related to this so-called KL calculus. So, Guoyin, thank you for accepting our invitation. So, the floor is yours.
Right, thank you, Radu. Thank you for the nice introduction, and thank you for inviting me, giving me the opportunity to give a talk. It's really a fantastic series. I have benefited a lot in listening to many of the talks in here. In particular, many of the researchers I admire of, and I have benefited a lot in reading their research articles. So I guess during the last few weeks, this really very beneficial for me because I was doing continuous online marking. So this 1 hour break really cheers me up and gives me a nice break, which is good. So and today I want to talk about something on Kurdyka-Lojasiewicz inequality and error bounds. And I think these two fundamental tools are actually now recognized are very important to analyze the convergence analysis for many numerical methods. But what I'm particularly today going to talk about is one aspect of them, which I think, at least in my very, very naive view, could be relatively less well exploited, which is estimating the exponents of these two important tools. Okay, and let me just briefly mention that these are based on joint work with some of my collaborators. These include Radu and Ming, also in the audience as well, and Boris Mutkovich, Tian Song in Dalat, and Ting Kei, and also Pei Ran in Hong Kong. Okay, so the outline of my talk will be as follows. Okay, see whether I can get this running. Okay, okay. So maybe I should do it again, sorry. So let me full screen mode. Okay, so first of all, I'm going to give the motivations just to explain what this talk's about, set the scene, and then I'm going to talk about the error bounds and the Kurdyka-Lojasiewicz inequality. And of course, the major part will be how do you estimate the exponents of them. And finally, I'm trying to conclude my talk. But as I often do in my talks, I will always feel these outlines a bit boring. So actually, this is actually my true menu is actually for you guys. So depends on where you are. So I'm trying to invite you either for lunch or maybe for a dinner. So the entry, just as I said, I'm trying to motivate the talk, give an explanation. And the main course I'm going to do is actually the two things, error bounds and Kurdyka-Lojasiewicz inequality. And that's my recommendation, is actually to try to estimate the exponents. And let's see how it goes in this case. Okay, and most of the talk is actually motivated by looking at a lot of structure optimization problem. By structural optimization, I mean optimization problem of the following form. So let's start with somehow a finite dimensional space. Let's denote it by calligraph X. And you can think of this underlying space as either the Euclidean space Rn, or maybe the space of a matrix, because later on we might deal with the matrix optimization problem. And in this kind of problem, so the objective function can be split as a sum of two functions. One I call gx, the other one I call hx. They are very typical, and gx often is the loss function, and you can use it to measure the data misfitting. And a very usual one is just the least squares function, which you're trying to see for a given observed data B and some given linear transform A, you want to see how your solution after the transformation AX, how much it deviates from the data you observe B in that case, right? And the second function involved, which is the H, actually I denoted by H in here, is a regularization function, which help us to promote some of our desired feature. So a typical one would be, for example, you want to promote some kind of sparse structure, or maybe sometimes the low complexity structure like the low rank structure. So typically this regularized function could be like the L1 norm if you want to promote the sparse structure of your vector solution X. And you can also use the quasi norm, which is when the LP quasi norm where P is strictly less than 1, of course, it's non-negative as well. And you can also use the cardinality function. And if it's a matrix, if you want to promote low rank structure, you can use the rank function or sometimes the nuclear norm, which means that you take the sum of all the singular values of the matrix. Okay, so you can see that most of the cases you will see the regularizer function is actually non-smooth. For example, just the most simplest one, the L1 norm, is not smooth. And some of them can be non-convex as well, just like the quasi norm when P is strictly less than 1, the cardinality function, the rank function are all non-convex. Okay, so you can see that basically the point I'm trying to make that the whole problem is in here, in general, can be both non-smooth and non-convex. Okay, so just to be concrete, let me give a few examples. So the most common example will be the Lasso problem. I think I probably have seen a lot of them. So you have a least squares function, half of x minus b norm square, and you want to promote sparse structure of your solution. So you add up with L1 norm in here. And here we multiply by a lambda, which is a parameter, which gives you the trade-off between the data classification or data misfitting and the sparsity of your solution. Okay, you can also work with the group Lasso, which is a generalization of the Lasso problem. So in these cases, so what happens is that you have, for your solution X, you have some predefined groups. So say, for example, you have M groups in here, and we index them by the index J1, J2, up to Jn, and their union is the whole index at 1 to n. Okay, and in this kind of application, you look for the least possible number of groups. So in that cases, you use this kind of group Lasso, which means that you take the linear combination, or I would say the non-negative linear combination of the Euclidean norm. Right? So in the very special case where M is just the total number of variable n, and each ji just be I, then you just reduce to the L1 norm, which is the Lasso problem. So it's a generalization of that. And you can also look at what we call a sparse generalized eigenvalue problem. So in this case, you look for somehow a solution for your generalized eigenvalue problem, and also they are sparse as well. And this kind of problem often arises in the, I guess, the binary data classification in using the sparse Fisher discriminant analysis, which the quotient really means that you want somehow the variance between the two classes is relatively large comparing to the variance within the classes. And the ratio just describes this, the thing I just said. Okay, so of course you can also deal with matrix problems. So the typical one for like the matrix completion problem, you do the least squares and then you're trying to promote the low rank structure. So then you add up with the nuclear norm in these cases. Okay, and again, the lambda is a trade-off parameter. You can also put the rank constraint in the constraint as well. So that also forms the least square with rank constraint. So all these problems serve as a kind of example which fits to the model problem I just said before. You can put them into that form. Okay, so now, so why this kind of problem is important? First of all, they have a lot of applications, machine learning, signal processing, and so on. And I guess most importantly, because of their solutions have low complexity, which is what we're trying to design, so that they can be easily stored, implement, and utilize, and so on. Okay, so all right. So in the typical method, or if maybe not the only method, but I guess they are quite popular, is to use the first order methods. Basically, they mean that the methods only involve the first order informations, and they are more scalable comparing to the dimension of the problem. Okay, and typical problem methods including the proximal gradient method, and somehow it can be the accelerative version as well, and can include the Douglas-Ridgeford splitting algorithm, the ADMM, the alternating direction method multiplier. So, okay, and just to be concrete, let me look at the proximal gradient method. So this is probably the most common method. So for this kind of method, so as we've seen before, our function can be decomposed into the sum of two functions. Here, the first function often is the continuous differentiable with Lipschitz gradient. And the second function, h, we often will require them to be proximal friendly in the sense that their proximal operator, which is defined in here, usually it can be easily computed. So if that's the case, the proximal gradient method, it just looks like you initialize at an arbitrary point x0, and you choose the gamma. Usually it's actually related to the reciprocal of the modulus of Lipschitz gradient. And then you do somehow first of all, you start with the current iterate, you follow the negative gradient of G, which is the forward direction. And then you do compute the proximal gradient of this one. And then you do the backward operation. So that's why proximal gradient method often sometimes also called forward backward splitting algorithm. Okay, and the proximal gradient method actually has a close relationship to many classical algorithms. For example, the alternating projection algorithm, which is used to solve the feasibility problem. Say, for example, if you have two closed convex sets, say C and D, the alternating projection algorithm you first project to the first set C, and then project to the second set D, and then repeat the process and continue on. Okay, and actually you could see that the proximal gradient method actually you can think of this as an extension of the alternating projection algorithm, at least in the convex cases. So the reason is that if you take the G to be the half of the distance, square distance function, and H to be the indicator function of the other set D, then the proximal operator just becomes the projection, which is projection of D. And if you compute the gradient of G, that's just at the point X, the gradient of Gx is just X minus the projection C of X. Okay, if you plug into here, and if you choose gamma equals to 1, this one becomes the projection of C in this case. So in that case, somehow the alternating projection algorithm just becomes a special case of the proximal gradient algorithm. Okay, so then we can use the alternating projection algorithm to demonstrate some of the interesting behavior of the proximal gradient algorithm in that case. Right. So let's look at some interesting behavior. For example, so these are very typical. Actually, for example, if we apply alternating projection algorithm for some degenerate cases, by degenerate case, I mean if you have two closed and convex sets and their intersection doesn't have interior. So this is the typical situation. I have two disks in here, one centered at, I guess, -1, 0, the other one centered at 1, 0. Both have radius 1. So they just kiss to each other, has an intersection point origin. Okay, so the intersection doesn't have interior point in this case. So there's a degenerate cases. So if you initialize in here, which is I guess 0, 2 in here, so you project to the first set, project to the second set, and then repeat the process, and you will see a zigzagging convergence to the intersection point. Okay, and because this case is just a disk and the projection has the analytical form, you can directly verify that somehow this sequence of xk converge to 0 or the origin in here, and the 0 means a 0 vector because of two-dimensional here, and also the norm is of 1 over root of k, so which means that it's a sublinear convergence in this case. Right. And on the other hand, if you look at the non-degenerate case, which means that somehow, for example, you can think of the intersection has interior, then by a classical result, for example, you can find in Hines and Jones' nice review article, then you would have linear convergence. Okay, and this has been pushed forward to the non-convex case as well by Agent, Russell, and Jerome, and also by Dima and Alex Fiorfi and Agent later on as well. So what they do is that they look at the local linear convergence and also under some generalization of the non-degenerate setting by involving the normal cone. Okay, so you will see that even just like applying the alternating projection algorithm in this case, which is a special case of the proximal gradient method, for different kind of situation, you might have different convergence behavior. Sometimes the sublinear convergence, sometimes just linear convergence. Okay, and the last example I just take out from one of the my recent work joined with Ming and Radu. we look at the sparse generalized eigenvalue problem we just mentioned before, and we apply somehow the inertia proximal gradient method to it. And you will see that somehow in here, actually, you will see that actually it follows a linear convergence, right? Actually, we prove in the paper that it always converges in a linear, right? So you will be wondering, actually, so given the typical method in here, sometimes it converges sublinearly, sometimes converges linearly, and sometimes it always converges in the linear. So what is underlying this kind of convergence behavior? And that's really motivated talk. So we're trying to understand what's underlying the convergence behavior of this numerical algorithm. Okay, and that forms the motivation talk. All right. And actually in the literature, there are two types of kind of fundamental tools for analyzing the convergence behavior. One is probably quite well known now, is called the Kurdyka-Lojasiewicz inequality. And its origin traced back to the Lojasiewicz original work in 1963. Okay, and this is actually, so the original form starts with analytic functions. So what it says is that if you start with a stationary point, then so you can find the neighborhood around this point, so that the gradient of gradient of the function around this neighborhood is bounded below by the change of the function values up to a suitable power alpha. Okay, and alpha is a rational number. In general, is unknown in this case. And unfortunately, this situation cannot be, in general, it's not true if you replace analytic property by a C infinity function. And here's the typical counterexample, which is, I guess, derived by Whitney. And actually, you can check taking the gradient evaluated at point 0 around this neighborhood and divided by the function f value of fx. By using the L'Hopital's rule, you will see that it's never bounded below by a suitable positive constant. Okay, so that's, you can check. And this has been extended by Kurdyka to continuous differentiable definable function. So definable function, basically an extension of semi-algebraic function and globally subanalytic function. So you can think of them just as finally maximum or minimum of polynomial function, if you will. Okay, and later on, Adrian, Jerome, and Aris extend them to non-smooth cases, which really broaden the application of this inequality. So that's why they bear the name of Kurdyka-Lojasiewicz inequality. Okay, and when they extend it to non-smooth settings, so what they need to do is, first of all, they need to replace the gradient by the subdifferential, and usually they use either the Clark subdifferential or the limiting subdifferential, and they have to replace the norm here by the distance from 0 to the subdifferential mapping. Okay, and that's the only change. Okay, so let me state the non-smooth Kurdyka-Lojasiewicz inequality, or sometimes called KL property in here. So what they do is that this property says if you have proper closed functions, then you can, at a particular point, x bar, we say the KL property holds if you can find a neighborhood, so here, we call V here, and also somehow a continuous concave function, which is one variable, and they are continuous differentiable on the open interval, and is I guess non-decreasing on the open interval as well. And then when you look at this one on the left-hand side, which is really is the distance 0 to the subdifferential of the composite function phi at f in here, which is bounded below by 1. Okay, and you might wonder how this actually relates to the original Lojasiewicz inequality. Is that, and for this one variable function phi, which they often refer as the d singular function, if it takes the form, which just phi s is c times s power 1 minus alpha. So you take the derivative, becomes this one power minus alpha, you throw to the other side. So you just get the original Lojasiewicz inequality. Okay, so you can think of this one as extension of the previous one over there. But of course, with the singular function phi in here, so the original exponent somehow disappears. Okay, but we somehow want to keep this exponent there. So that's why we define the KL exponent just as this one. Basically means that somehow the singular function just take the form of the previous one, c times s power 1 minus alpha. Okay, if that's the case, we will call the corresponding alpha to be the KL property with the exponent. Okay, so that's what we're going to do. And if And if somehow the function have this property with exponent alpha for any point in the domain of the subdifferential, we just say it's a KL function with exponent alpha. Okay, so once you have this one, and this is the typical result you will see in the literature. So if you have a bounded sequence generated by the algorithm, for example, think of the proximal gradient algorithm if you want, and you can work out that the corresponding Marie function that captures the behavior of your algorithm, if it is a KL function with the exponent alpha in here. And depending on the range of the alpha, you can have different behavior. If alpha is 0, then the sequence converges finitely. If it's between 0 to 1/2, and 1/2 is included in here, then it converges in a linear rate. And if alpha in the open interval between 1/2 and 1, it's just a sublinear rate, and the order is actually related to the alpha, which is explicit in here. Okay, so you can see that somehow the convergence rate really depends on whether you can find out what are the exponents that involve in the KL property here. Okay, and you can verify that. You can see in the literature, very similar. You can check if the proximal alternating minimization algorithm. And also recently we do it for the Dockers-Ridgeford algorithm as well. Okay. All right, so now let me move on to the second tool, which is also important, which is the error bounds, which is a nice and which is also very nice in here. So let me start with it just could be a extended real value function f. And let me just, for simplicity, let me just look at the finite dimensional space Rn. And in many cases, you can reformulate your solution set into just simple as a linear inequality system. Okay, so let's try to look at it here. So what do we do for error bounds is that first of all, we're trying to judge for a given point x, whether we want to see x is a proximal solution of this inequality system or not. So what we mean is actually we're trying to estimate the distance from the given point x to the solution set, which is denoted by f less or equal to 0. Okay. In general, it's actually hard to estimate because if you want to estimate this distance, you need to have a good information how the solution looks like. So alternatively, what we're going to do is that we just measure the function violation, which is take the fx, plug into the value x, compare with 0, take the maximum. Because if this one is 0, then you know this actually in the solution set. If this value is large, maybe you will think of them the point is far away from the solution set. So let's formally formulate it. So we just basically look for an error bound in this case. So basically we're trying to estimate the distance to the solution set in terms of a computable residual function, maybe up to some suitable power alpha. Okay, and it can be either holds locally or globally, depends on the situation. Okay, so this is actually what the definition is, but I think I just explained them. So global one basically means that this inequality is true over the whole space. Locally means that it is true around a neighborhood of the given reference point. Okay, if the exponent alpha in here just 1, we often call them Lifshitz type error. Okay, so they have been useful in a lot of cases. First of all, useful in finding the convergence properties and sensitivity analysis, and also identify active constraints. And they can also be useful in finding maximum monotone operators as well. Right? Because the idea of quantifying something which is hard to measure by using computable residual function is a very nice approach, and so that you can quantify them using the Marie function approach. Okay, so there are some typical known results. The most celebrated one would be the Hoffman error bounds, which says that Lifshitz type error bound results always true when your function is maximum of finitely many affine functions. Okay, but unfortunately, it is true. It is failed in general for nonlinear function. Here's a simple counter example, and there's many developments. There's long list of authors in here. Okay, but in quadratic case, things are very nice. So first of all, I guess by Tom Law and another law, his collaborator, they show that if you have a complex quadratic function, then global error bound holds with exponent 1/2, which is very explicit in terms of the exponent. And the local error bound holds for non-convex quadratic function as well. That's a result by Tom Law and Jan Storm. And there's an open question, as far as I know, is still open. In this case, they will ask, what happens when the function can be expressed as finitely many quadratic functions, which is not convex? Actually, the conjecture, it should be 1 divided by 2 power m, where m is the number of quadratic functions involved. Okay, so that's the conjecture. Okay, so there's a nice interplay between the KL inequality and the error bounds, at least in the convex case. And this is done by Jerome, which is a very nice one, where he showed that they show, I think there's a group of authors over there, if the convex function has a KL exponent with alpha, then it's even only if a local error bound holds for the function f, subtracting the infimum of f. Okay, because here we actually assuming that the argument of f is non-empty. And the exponent actually also has a relationship. If the KL exponent is alpha, then the local error bound with exponent, which is 1 minus alpha. Okay, so that's very explicit here. So which means that somehow, if you can work out the local error bound, the exponent of that, you can also work out the KL exponent of the alpha, at least in the convex case. Okay, so which is very good. All right, and then the question really for us is how to exploit or estimate this exponent, because if you don't know the exponents, then that's not very informative. Then you don't know exactly what's your convergence rate and so on. Okay, and the strategy we're going to undertake is just the two things. So first of all, trying to explore the polynomial structure, which is a nice one. And the second one I would call the live-in and projected approaches, which is naturally arises when you do SDP relaxation and so on. So that once you can lift it up to a high dimensional case, and so that the case is more clear, for example, you can look at the semi-definite representability, or maybe sometimes C2 reducible structure. Okay, right. So good. So, but the motivating example for me to do, so let me start with this one, very simple. And that's really explain why I want to look at, first of all, the polynomial structure. So let's look at this simple case. Remember this one, let's first look at the convex case because the example is convex in here. And the KL exponent and the local error bound with exponent in this case are equivalent in this case. Right. So if I look at function f x squared, so if you look at the error bound in here, you can verify that the exponent is 1/2 very explicitly because the solution set is 0. And the function take the 1/2, just the absolute value of x. So you can bound it by just the coefficient 1 over there. Okay, and that's also compatible with Thom law's result, which is the exponent just 1/2. Okay, but with just almost the same procedure by manipulating the 2 to power d, where d is an even number, you get a convex polynomial. And then with the same analysis, you will see the error bound holds with, again, a very explicit exponent, which is 1 over d. Okay, so although this is a very simple example, hopefully this kind of hinted us that with polynomial setting, so somehow you can hope that you will get a very explicit exponent in terms of the error bound, or maybe the KL exponent in here, because it's a convex, right? And also the exponent should depend on somehow the degree of the polynomial involved. Okay, and in general, it also should depend on the dimension as well, because here it's a one-dimensional, so the dimension that you couldn't see in here. Okay, but in general, it depends on two things. One is the degree, and secondly is the dimension of the underlying space. Okay. So the question is that, so can we extend this one from the quadratic cases to the polynomial cases? And first of all, we look at the convex setting, and if so, can we do the non-convex as well? Okay, right. And here's are the recent development for in the polynomial setting. I will summarize them and then I illustrate it, at least in one case, how you do that. And then you can figure out that the other cases follows in a similar strategy. Okay, so here's a summarization. So first of all, when f just a convex polynomial with degree d, you would have a global error bound with just 1 over d minus 1 power n plus 1. And you can see that if the d is just 2, then you reduce to Thom law's result, which is 1 over 2. Okay, and also when the dimension n is 1, you just get 1 over d, which is exactly the previous motivation example. Okay, and you can also look at the convex piecewise polynomial in terms of global error bound. What you do is just by convex piecewise polynomial, I mean a polynomial which you can divide domain in terms of finite union of polyhedra, and on each pieces it is a convex polynomial. Okay, so the way we do it is actually basically we just look at each pieces and then look at the cases and then glue it together. Then it follows from the first result. Okay, so that's why you see they have the same exponent over there. Okay, and together with Liang Jin and also John, unfortunately John passed away now, but we look at the case when f is a maximum of finitely many convex polynomial. And in this case, we couldn't get the global error bound. Actually, the global error bound in this case in general fails. We have a counter example, but local error bound still holds. And it also has somehow an exponent in here, which is also, again, determined in terms of the degree involved in the dimension n over there, although it's a little bit involved over there. And actually, we also have an example over there saying that somehow the exponent here can, in general, is relevant in the sense that you can have an exponent which is of the same order of growth, which is the d power n, 1 over d power n, which in some sense is optimal in some sense. Okay, and moving to non-convex cases, as I explained, so you can look at maximum of n polynomials, and actually they can be non-convex. This is a joint work with Boris and Tenzong. Again, there's exponents in terms of the degree d and the dimension n, and also the number of polynomials involved in here. Actually, here and in here we look at the KL exponent rather than error bounds over there. Okay, but let me also mention the first result in here, which I didn't say. It's actually Jerome's very nice work, where Jerome nicely observed the interplay between the error bounds and the KL exponent in the convex case, and then he applied the global error bounds we mentioned before to the KL exponents, and he obtained the KL exponent, which is the one we just mentioned, 1 minus the exponent we just mentioned over here. And this one actually applies to, for example, the least squares function with the L1 regularization, because that's a particular case of the convex piecewise polynomial. Okay, so that's why you see this exponent over there. So very nice work over there. Of course, in Jerome's paper, he also obtained the complexity as well, which is he had, I guess, more additional information over there. Okay, but at least let me explain or illustrate how you can do it. So I guess this may be more interesting. So let me explain, at least illustrate how you can get the error bound or KL exponent for the case of convex polynomials. All right, and then the other cases you can somehow envisage they follow in a similar strategy. So, and then of course, then the question you might challenge me is that why you need to really worry about polynomials, right? So, although I'm motivated by a simple example, but polynomial optimization is one of the motivation, and they have been studied was a very popular topic in the last, I guess, 10 years, pioneered by Jean Lassalle and Pablo, and further developed by Dickler, Monique, Lauren, and Jia Wang as well, where they can construct a sequential semi-definite program approximation scheme to solve the polynomial optimization problem under what they call the Archimedean assumption. Okay, so but what I want to say is that actually polynomials also have very good analytic structures, which sometimes we miss as well. So here's a few of them. Actually, I will make use of some of them later on. So the first one, which is I like very much, although it's very easy to state, but actually I think it's very delicate to prove. It's actually a very nice result by Belousov and Clarté back in 2000. It's a Frank-Wolf result showing that as long as you have a convex polynomial, if it's bounded below, then your solution always attains in here. Okay, and this is actually not shared by a general convex function. For example, you think of exponential function, then it's always bounded below by 0, but actually you never attain the solution. So which means the convex polynomial is really special here. Okay, and the second result basically says that if you have a stationary sequence, then it's also a minimizing sequence. Actually, we do it back in 2010. Okay, and the third property is actually located in a nice book by Mark Tabou and Oslander, which says that if you have a vector v so that the resection function takes the value 0, then actually the function actually takes a constant value along this line. Okay, and if you, in case you forget what is the recession function, here's a definition here. Okay, so here I'm going to make use of some of this property to show you how you can do the convex polynomial setting for the error bound. Okay, and let me just recall you what the error bounds results in here. So we have a convex polynomial on Rn with degree d, and this is basically the result for the global error bound with the exponent just this d minus 1 power n plus 1 and take the inverse. Okay, and as I mentioned before, it agree with Thom Law's result in the d equals 2, and also agree with the previous example where the dimension is 1. Okay, and let's see how we prove it. And actually the proof is a bit involved, but in terms of ideas, very simple. It's actually based on mathematical induction. Very nice trick. When I was a big fan of that when I was a high school student. Okay, okay. And what's underlying that is actually a very nice growth property for polynomials, which I'm also going to use. It basically says that if you have a polynomial, and with degree d, and has additional assumption, which is a bit annoying, but later on we can circumvent. Okay, if the origin in here is a strict local minimizer, okay, then around the neighborhood of this local minimizer, then the x to the locus of the 0 set is bounded above by the function value with the suitable power rho, and the rho is explicitly the exponent you have seen before. Okay, and that's where the exponent comes from, I would say. Okay, and this is a nice result by Guoyin in 1999, and later on was refined by the a famous algebraic geometer Janos Kohler as well to the semi-algebraic cases, but again under the strict local minimizer. And you can drop this strict local minimizer assumption, but somehow you get a weaker estimate, and that's the work by Kurdyka and also with Boris and Farnsberg as well. But here I'm just going to make use of the Guoyin result here. Okay, and let's see how we can do it. Okay, so the strategy is very simple. So we do the induction on the solution set. Okay, so let's look at the dimension of the solution set f less or equal to 0. If the dimension is 0, then you get a strict minimizer. Then I can safely apply the Guoyin result. Then I'm fine. Okay, so now I'm doing the induction in here. So suppose this result is true when the dimension k is equal to p. I look at the next case with p plus 1. So what I would do is that I will argue that either the state condition holds, which the error bound holds in that cases, or you can find the direction v, so that along the direction v, the recession function take the value 0. Okay. Now I'm going to make use of the Mark-Tabou's result, saying that the function will take a constant value along this line. Then in that case, you can modulate this constant space and then reduce the dimension by 1. Then use the induction hypothesis, you arrive what you want. Right. So there's a very nice proof, but although it's quite involved later on, but in terms of proof, it's very nice and simple as well, just by induction in this case. Okay, so that's how we do it. So essentially, you see what we do is that we make use of some fundamental algebraic geometry results and use some nice structure about the polynomials, either the recession property in here, or sometimes later on, you can make use of other properties as well. Okay, and that's the strategy we're going to do. So exploiting the structure, polynomial structure, sometimes the convexity structure as well, or the recession properties, and together with the polynomial result in the algebraic geometry literature. And that's the general strategy. And this also is also true in a non-convex case as well. We basically adopt the same strategy. Okay, at least I illustrated you how we can exploit the polynomial structure in this case. So I'm going to look at the other strategy in this case, which I will call the lift and project approach. Okay, so the second approach is called the lift and project approach. What we do is actually just like the relaxation idea. So we're going to look for somehow a lifted function, fxy. So we have two variables, x and y in here. And we write function fx as the infimum, or you can say it's optimal value function of the bivariant function fxy. Okay, and it has the name of inf projection because the strict epigraph of f has a relationship with the strict epigraph of the bivariant function capital F here. Okay, so they have been used a lot, particularly in the if you are familiar with the duality approach, the perturbation approach is actually exactly of this form. But actually, it was very useful for SDP relaxation because basically you can characterize very complicated function using optimal value of conic program. So the idea is basically you lift the function somehow as optimal value of a conic program, and then you can use the idea or the structure of conic program to study the corresponding complicated function. Okay, so that's the general idea. So we have a result somehow relating the KL exponent with the corresponding inf projection. So basically, if your function fx has this kind, is the inf projection of the bivariant function capital F. And assuming some technical assumption, basically we need the bivariant function to be level bounded and uniformly in one of the variables. So that you will see that the argmin function is always, the solutions always exist, okay? And also the subdifferential is non-empty. And if your bivariant function of the lifted function has the KL exponent alpha, at every point, which is x bar cross the solution set at the appropriate point x bar, then this inf projection f has the same, is satisfied the KL exponent with the same exponent alpha. Okay, so what we do is basically we just use the variational formula for these subdifferential of this inf projection, so that you can estimate the distance from 0 to the subdifferential of x in terms of the bivariant function, and you just proceed. Okay, so it's a consequence of the variational formula of the subdifferential of the inf projection. Okay, so what is it about? So because now you can do a lot of things. For example, if you look at those functions can be represented as semi-definite programming. For example, if your function is what we call the linear matrix representable, in the sense that its epigraph can be written as this linear matrix inequality for some matrix involved with a suitable dimension. Okay, then using this kind of idea, then your function actually can be lifted as somehow an optimal value of the semi-definite program. Then you can use the results, for example, in error bounds of the semi-definite programming to study the KL exponent. Okay, so that's the general idea. But let me just give you a bit of examples of the linear matrix inequality representable function. For example, the L1 norm, L2 norm, convex quadratic function, or indicator function, second order Cohen, and so on. Okay. So now let me give you the first result. This is a joint work with Pei Yan and Ting K as well. So if you have a sum of finitely many linear matrix inequality representable function, and if you have your linear matrix inequality representation, they satisfy strict feasibility condition, okay, so that you can make duality and so on. And also the second condition is more important. We are assuming the strict complementary condition satisfied, which means that 0 is in the relative interior of the subdifferential at the point x bar. Okay, then you will see that f satisfies the KL exponent 1/2 at the point x bar. Okay, and how do we do that? And the idea of the proof is very simple, but actually you will see later on all the strategy would be very similar. So let me explain here. So what we do is that we write the function fx as the inf projection of this form. So what we do is that we write this one as so inf norm of t with the constraint that t is bigger or equal to sum of si, each si dominates fix. Okay, and remember that this is the epigraph of fi, and they can be rewritten as a semi-definite program constraint. So what this infimum projection is really an optimization, actually a semi-definite programming problem in this case. So you minimize the linear function, which is t here, over a linear matrix inequality constraint. So it's a semi-definite programming problem. Okay, so what we do is that we just argue that the resulting semi-definite programming problem has a singular degree 1, okay, which is by the strict complementary condition. And you can use the very nice result of the error bound result by Storm to argue that you have the error bound with exponent 1/2. Then because of the convex case in here, so that's why you also have the KL property with exponent 1/2. So that's how we prove it in general. Okay, so basically you lift it up, and then you use a nice structure of the conic program, and then you use the interplay with the exponent of the error bound and the KL exponent. So that's all it is. Okay. So of course you can look at further things, right? But before I do that, let me mention this cover a few examples. Some of the examples you have seen before. For example, the group lasso is a particular example because these are the linear matrix inequality representable function because convex quadratic, and L2 norm is LMI representable as well. Okay, so the sum of them definitely falls into the previous form. And you can also look at the group fused lasso, which is just the least square lost convex quadratic function, linear combination of the L2 norm, and also this one is just a linear transform of the L2 norm in here. So they all fall into the previous cases. Okay. So the next case is actually more interesting because sometimes we want the matrix optimization problem where we look for somehow you can have the nuclear norm here. By nuclear norm, I mean the sum of the singular values here. Okay. And of course, we can take the sum of linear matrix inequality problem. In here, we can adopt a similar strategy, but we make use of the semi-definite program representability of the nuclear norm. Okay, and that's how we do it. So again, we lift it up as a semi-definite programming problem, and then we make use of the error bound result of it. And what you can do is that you can show the similar result. Again, under very similar conditions, you can prove that the function is a KL property with exponent 1/2. So which means that if you apply, for example, proximal gradient method to in here, if these conditions are satisfied, then you can actually obtain linear convergence rate. Okay, and I must emphasize that in the very special case when m is 1, and this is the least squares function, and you can also obtain this result by using a nice result from Anthony Su and Ziray Zhou in 2017, where they look at the proximal error bound over there. Okay, so that's what I mentioned. Okay, and actually you can even go beyond the semi-algebraic structure, because the what I mentioned about the positive semi-definite cone, this SDP is semi-algebraic. You can even go beyond that by looking at the C2 cone reducibility. So the C2 cone reducibility is a nice structure that was introduced by Shapiro. So what they do is actually, they basically say that a closed set D is C2 cone reducible if you can find a neighborhood and also a closed convex pointed cone and a mapping, so that the mapping is twice continually differentiable and the derivative mapping is onto, and around this neighborhood, the set D can be represented as this conic constraint. Okay, and the examples of them include polyhedras, second order cones, positive semi-definite cones, and also the sets were defined by twice continuous differentiable functions, where when the linear independence constraint quantification is satisfied. Okay, so with this one, we can also show that if your function have this kind of following form, so the function can be decomposed into a composite structure where L is a strongly convex function with local Lipschitz gradient, and composite is a linear map, adding with a linear function, and also a support function of a C2 cone reducible closed and convex set. Okay, under a relative interior condition, you can also show that the KL exponent is actually 1/2 in this case. Okay, so also the strategy is also very much similar. You lift it up as a conic programming problem, and then you use the error bound for the conic program to do that. Okay, and of course, sometimes the relative interior condition can be dropped, because what we require is indeed the bounded regularity condition, and this is actually true when the normal cone is actually a polyhedron. Okay, some examples for that. So you can look at the positive semi-definite constraint, because if you remember, so if I take the D to be the positive semi-definite cone, it is a C2 cone reducible, then the support function of the positive semi-definite cone will be the indicator function of this dual cone, which is the positive semi-definite cone itself. So you will arrive at the semi-definite cone constraint of this kind of function. Okay, you can also look at the scattering P norms in this case, whenever P is belong to these cases. Okay, you can also get this KL exponent, which is 1/2, right, as long as the relative interior condition is satisfied. Okay, all right. So let me also mention that this approach also allows us to consider other models. For example, you can also consider the rank constraint as well. And you can also consider the sparse generalized eigenvalue problem, which I mentioned before. And this is actually how we do, is actually we somehow use this kind of lift and projected approaches, related this one to the quadratic functions, and then apply the KL exponent for the quadratic function to derive that the KL exponent for this class is actually 1/2. So that's how we arrive at linear convergence rate when we apply the inertia proximal gradient method to this model. Okay. So now I think I can conclude. Okay, so I'm trying to convince you that the structural optimization problem, like the sparse optimization problem, is an important and challenging topic. And first order method is an often widely used method in this context. And the convergence rate really hinges on the either the error bound exponent or the KL exponent of a suitable potential function. And somehow one approach in obtaining this kind of exponent is to develop some kind of calculus rule, like the in projection rule we mentioned here, and so that you can lift it up, or you can exploit the underlying polynomial or conic structure. Okay, so I haven't mentioned a lot of things because due to the time constraint. Some of the things I didn't mention, for example, you can also study the convergence rate in terms of what they call the proximal error bound in the sense of Thom law and Portion. And this has been exploited, for example, by Dima and Adrian, and also Ziray and Anthony, and also we also tried a little bit with Tim K as well in a different paper as well. And of course, the KL exponent and KL inequality has very nice relationship with the metric subregularity or metric regularity, right? The error bound is actually just a special case of metric subregularity. So you can expect that they must have some very close relationship. And for example, you can look at Jerome and Aris and their co-authors' nice article here. And of course, the Kurdyka-Lojasiewicz inequality actually continues to hold in infinite dimensional space, and which they call the Simon-Kurdyka-Lojasiewicz inequality. And actually that can be true in metric space, Banach space as well. So which I didn't cover in here, which you can also look at this nice article over there. Okay, so finally, just some minor questions which I couldn't crack in these cases. For example, we'll see that the lifting projected approach may depend on the representation of the lifting. So is there any optimal lifting in here in the sense that maybe there's, I guess the least auxiliary variable may lead to better estimate in here. So is there an optimal lifting here? I'm not sure at this moment. And the other question which is important is that what are the modulus that involve in the error bound and KL inequality? What I mean is those proportional constant, because for example, when you have a linear convergence rate, if the linear rate, if the R is actually close to 1, sometimes it's just very hard to distinguish with the sublinear rate. So in that case, the modulus actually is also important as well. But I must say that computing the modulus, even the Hoffman error bound's modulus is a non-trivial task in general. Okay, in the literature, I think most recently, there are a very nice article by Javier Pena and Luis de Luga, where they use the mixed integer programming problem and also the MPEG, the complementary constraint techniques to compute the modulus of the Hoffman error. Okay, and of course, you will see that the results sometimes hinge on the relative interior conditions. Whether this kind of condition can be relaxed or not is also an interesting question. And do we have further calculus rules? And also come back to the previous conjecture of Tom, Low, and Storm, whether the conjecture is true or not with the local error bound with exponent 1 over 2 power p, where p is the number of quadratic functions involved, which I also don't know as well. So with that, I think I should stop. And thank you very much. Let's stop with the reference in here. Okay, thank you.
Thank you, Guoyin. Thank you very much for a great talk. Yeah, so very nice overview, very nice results. You mentioned a lot of literature. So it is a very nice topic, and it was a very nice topic in the last 10 years in our community. So it is time for questions. Jerome.
I think Radu can ask a question.
Yeah, let us start with Jerome, and then yeah. So Jerome was the first who asked a question in the chat. Jerome, do you like to unmute your microphone, or should I read the question? Okay, so Jerome is asking, so can you exploit the infimum trick to analyze KL exponents of Legendre conjugate?
It's a very interesting question. So the differential conjugate, so it's a supremum form, right? So supremum of a linear functions minus the function fx. Actually, so we actually with Boris and also Tim Song as well, we have attempt with a supremum rule as well. But then the supremum rule relies on the so what we did is actually we introduced auxiliary variable to reduce to using Lagrangian multiplier. And then we treat the Lagrangian multiplier as also part of the variable of the auxiliary function. So, but the trick actually has a drawback in the sense that, so it depends on how many auxiliary that introduce a lot of auxiliary variable. So I guess the short answer is possibly yes, but I'm not sure whether the corresponding exponent will be sharp or not, which I'm not sure. I think that's my short answer to that. But I think it's a very good question to explore as well, I think.
I agree. Yeah. The thing.
Hi, Radu. Hi, Guoyin. This is a wonderful talk, in particular, given the time, right, in the midnight. So, Guoyin, here's the question. You talk about the nuclear norm regularized problem.
Right.
You prove this the error bound by lifting the nuclear norm optimization problem into SDP problem. Now, the lifting has one problem. You don't keep this constant non-degeneracy, right? For example, at the origin point, you do not have LRCQ to hold. So when you do the lifting, particularly for nuclear norm to SDP, I think lots of good properties would have lost. Have you observed this? Have you thought about this issue now?
It's a very nice question. So it is true that when it will, I mean, first of all, I think the lifting is not unique, first of all. I mean, for some of the lifting, it is possible that some of the nice structure or property is lost in the higher dimensional cases. So in that case, it is true, as you mentioned, sometimes can be sometimes dangerous to do the lifting in that sense. But of course, I mean, I think then there's two things one could do. First of all, how do we choose the corresponding lifting so that one could preserve this kind of nice property? That's the one thing one could do. And the second thing, which is, I mean, in this case, I think part of our analysis is trying to argue that somehow this kind of structure is preserved in some sense. For example, what we prove, I think, in the nuclear norm cases, if I remember correctly, is that because of the strict complementary conditions, and then you can preserve some of the important property over there. So, but of course, yes, I think,
agree. Yeah.
So,
I think
but
you assume this kind of strict complementarity, perhaps is okay. As you mentioned, that is very risky, but particularly numerically, if you do the lifting, then computationally, so essentially you are seeing that you are going to leave the second order Coulomb problem to be a SDP problem, right? Because the nuclear norm is only one row or one column vector. So essentially the nuclear norm just you get a single order Coulomb problem, right? So you do the lifting from single order Coulomb to SDP computationally is very, very risky. But for your theoretical results, it's okay. But for others, I think we agree with each other. It could be risky business. And thank you very much. Yeah.
Thanks for the question.
Thank you, Frank.
Yeah, thank you.
I have a question.
Oh, Bruno first, and after Manuel. Yeah. So Bruno raised hand. Manuel, sorry. Yeah. Okay.
Yeah. Oh, sorry. Thank you for the talk. There are two things I wanted to confirm. Can you show again the? I think the first slide where you had the lifts to SDP and the strict complementarity condition.
Is this? Let me see. Which this one?
I think it was.
I'm not sure which one you have. Maybe this one. I'm not sure.
Yes, I think it. Yeah. Okay. This one is also okay. So just to confirm, you mentioned about the singularity degree, but I guess you're talking about the singularity degree of the optimal set. So you use strict complementarity to argue that the singularity degree of the optimal set is one.
It's one, I think.
So yeah, and so what I really wanted to ask is related to, I guess, one of the open questions you mentioned, is because Sturm zero bound itself does not require a strict complementarity. When you take a look at the only thing that happens is that if the singularity degree with respect to the optimal set is not one, you get a worse Hilderian error bound. So did you take a look about the possibility of trying to keep strict feasibility, but just relax strict complementarity? So yeah.
Yes, very nice question. Actually, you could possibly relax the strict complementary condition, but the price you pay is that the corresponding SDP that will depend on your singular degree. In that case, you will get 1/2 power d, and d is the singular degree of the resulting semi-definite program in the lifted space. But of course, in that case, I'm not sure actually how do we estimate the singular degree for the lifted SDP in that case. That's why we haven't explored on that direction, I think.
So the singularity degree of the optimal set, there are a few estimates of them. So of course, I guess what would happen is that in the end, you get a result that is written in terms of the singularity degree. But this by itself, I guess, so, okay, so, and then I guess the final.
Yeah, of course, I think I remember the singular degree is bounded by the dimension -1, right? I think for the SDP, if I remember correctly.
So on a better estimate, I guess, is the yes, that you mean if it's by n, it's bounded by n-1, for example.
Right.
So you have this kind of bound. So do you think you just get a similar result for the exponent, but with the singularity degree embedded in it?
Yes, I think in that case you will get the exponent, which is not, in that case, it's actually dimension dependent, I would say. But of course, you can possibly relax the strict complementary condition. I think that's what I would expect. I think.
Oh, so okay, just a quick remark. So there are other bounds on the singularity degree in terms of the dimensions of the spaces that the linear spaces that are composed that are used to express the set. So I'm not sure if this could also be helpful, perhaps.
That would be interesting. I haven't looked at the facial structure yet, so this would be good because I know that facial reduction is the great trick in handling semi-definite programming problems. So it's good to explore that, I think. Thanks for the suggestion.
No, thank you very much.
Thank you very much. Manuel Bomse.
Yes, thank you, Guoyin. Also, I join all the previous speakers to thank you and congratulate you to the high standards of your presentation. Can you go 2 slides further, please?
2 slides. You mean going back or going forward?
Forward.
This one?
Yes, 1. Okay, no, 1 is enough, or 2. Yeah, doesn't matter. So I wonder whether this C2 cone reducibility would also apply to the copositive cone.
It's a good question. So I'm not sure actually. So
what would it imply then? Of course, probably it's not.
I'm not sure actually. Let me have a look at the definition. I'm not sure.
It was so quick for me, so I could not figure out. So,
so it's a good question. I'm not sure. I must say.
Because you mentioned a lot of very nice tractable cones, and I was wondering whether this could be transferred to nasty cones. Like
so it's a good question. Maybe I think I would. I'm not sure at this moment. I would say it's a good question to investigate. I would think.
Thank you. Can I ask another question, which is more lower level, just for somebody who is completely new to this field? So, if as far as I understood, both the error estimates, the error bound estimates, and the KL theory would help us to establish convergence rates, right?
Mm-hmm.
So is there, I could not figure it out quickly, but probably it's a trivial question. So if you manage to transfer by your theory some of the error bound estimates to KL with a certain exponent, did you get by this means, and then apply it to the convergence rates, do you get the improvement, or do you get the same results as you would get directly with the error bound estimates?
I would think possibly I would not get any improvement. The only thing is to identify what are the convergence rate, I think, in this case.
So it would be, what you would say is you embed KL into a larger framework which was previously directly attacked by error bound.
So what I would say, so I mean, first of all, the equivalence of the error bound and KL exponents only in the convex cases, I think.
Yes.
So in the non-convex case, in general, they are not equivalent. So, but ideally, you go ahead for the KL exponent in that cases. So, but I think what we are showing in here is trying to identify the exponent in some of the cases previous possibly is unknown, I think.
Yes.
So that you can look at the convergence rate when you apply a suitable algorithm. I think that's
I completely agree that this is a very valuable contribution to the theory. The question is, what implications does it have for the rates, for closer to applications or to algorithmic view?
I see. So you're asking what's the implication for the algorithm? I think that's a good question. I think, I mean, of course, this research is more, I think, more mathematical, trying to understand the convergence rate in here. But I guess if you can identify for example, the convergence rate, maybe you can use this insight to develop new algorithms so that you have better convergence rates, or maybe you can build a new model so that the linear convergence rate always holds. Maybe then you can design better algorithm or better model in that sense. I think that's possibly one possible potential approach.
Thank you very much. Thank you.
Thank you. We have another question in the chat. So D1 Wang is asking, do we have a sum rule for KL exponents?
It's a very good question. Actually, I think in general for non-convex functions, the sum rule actually breaks down. You can easily construct two functions. When you sum them up, then the exponent actually suddenly jumps. So, but in the convex case, I think there's a very nice sum rule actually derived by Dima and also Adrian. What they do is that they look at somehow the dual. I think they also assume some, I guess, the dual strict complementary conditions. And as long as this kind of condition is satisfied, then you can have the sum rule so that the exponents can be computed by looking at each pieces, what are the KL exponents. But I think it's a very valuable question and also contribution by Dima and Adrian as well.
Okay, and I have a question going. So is there a suitable, useful KL result in alpha-dimensional spaces? Since I'm talking to people in optimal control and they would like to apply this KL theory, beyond the five-dimensional case. Is there something which can be said in alpha-dimensional spaces?
As far as I know, I mean, of course, there are KL inequality in general for infinite dimensional spaces, but in terms of exponent, I think the best I can aware of, maybe of course I may be very naive in here. The only thing I knew is actually in the quadratic cases, which you have say a bilinear kind of mapping, and if somehow the range is actually closed, you can get somehow the exponent is 1/2, I think.
Okay.
So I think I remember seeing results along this line, I think. Okay. But of course, I mean, I'm not sure for the other more general or more complicated situations.
Okay, thank you, Guoyin. So, there is, okay, so last question from Bruno Lorenzo. Yeah, sure, go ahead.
Sorry, so a quick question. So are you aware of results, for example, okay, this might be a bit vague, but for example, you have linear convergence, and from that you are able to obtain that the exponent is 1/2. So in a sense, trying to go the other direction of the pattern that you mentioned.
Okay. So it's a very intricate question, but I mean, I am not particularly sure, because one thing actually I can say is that actually in Anthony's paper, he has a very interesting example where he shows somehow the relative interior cannot be dropped. But what he shows is actually the corresponding error bound in the sense of Tom Low and Paul Chung actually fails, but still he observed linear convergence in the numerical experiment. So with the view of his example, which that's why my answer is I'm not sure about whether this is actually true or not. So.
Okay.
But of course, it's an interesting question to examine, I would think.
Thank you.
Okay, thank you very much. Then let us stop here. Thank you, Guoyin, for a great talk. So
thank you.
So we will post the slides and the talk on the video on the website. And thank you again. Have a good night, Guoyin.
Yeah, sure.
Okay. Thank you, the participants for attending this nice talk. And I just want to announce that the last talk of the second season of OWOS will be given by Yaxiang Yuan from Chinese Academy of Sciences. And there will be a break, and then we'll continue in January with the third season. First speaker will be Diatush. But as I said, we will have a last talk next week, given by Yaxiang Yuan. So have a nice week. Thank you, Guoyin. It was great. Great talk. Great event. And have a good night. Bye-bye. Thank you.
See you.
See you.
Thanks, Guoyin.